Suppose a 12 kilogram mass is sliding down a frictionless incline. The angle of the incline is 35 degrees. Our goal is to find the acceleration of the mass. For the first time, we have an object whose motion is not in the horizontal or in the vertical. It's down an incline. Still a one-dimensional problem, but naming the axes can be a little bit tougher if we wish to do that. And we're going to try this. We're going to kind of make a coordinate system that's tilted and compatible with the motion. So we will have one axis. It's coming down. We'll draw it through the current location of the mass. And that axis, we'll actually call it the perpendicular axis. And I'll even choose the sort of downward direction to be the direction of that. Use a little perpendicular symbol to show what's going on. And down along the incline, well, I'll just kind of extend it out in that direction. That's going to be the parallel axis. We'll draw two little parallel lines to indicate that. The mass is moving and accelerating because of the gravitational force. So let's try drawing that in. Gravitational force coming straight down. And that's the weight of the object is going to be mg. And that'll be 12 times 9.8. So the weight is 117.6 newtons. While there's the 35-degree angle that's drawn for the incline, we can look at the geometry, the right triangles and whatnot, and actually figure out that the angle here, the weight relative to the perpendicular axis, that angle is also 35 degrees, which will come in handy. The weight, as any force, can be broken down into components. The weight can be broken into a perpendicular component. If I draw coming straight across, well, in some 90-degree sense, straight across to that axis, this is going to be the perpendicular component of the weight. And that, well, if we look at the cosine of 35 and looking at this right triangle, cosine of 35 would be the adjacent, which is the W perpendicular, divided by the hypotenuse, which is the weight as a whole, the 117.6. Where that tells us that the perpendicular component of the weight is going to be 117.6 times the cosine 35 degrees, which works out to be approximately, in my notes somewhere, 96.33 newtons. And we can take the weight and look at the component up in the parallel axis. So we'll draw up in that direction, makes a 90-degree angle. And this is going to be the W parallel. And the W parallel, I can kind of write it out this way, it's going to come from the sine of that angle. It will be 117.6 times the sine of 35 degrees, or that will be about 67.45 newtons. And looking at these components, well, for the motion of the mass on the frictionless surface, only the parallel part of the weight, the 67.45 newtons, contributes to the motion and the acceleration. However, later when we introduce friction, we're going to see that the perpendicular, the 96.33 newtons is also significant. In fact, if we wanted to consider the force that the surface applies to the mass, we'll sketch that in just for kind of future talking purposes. The force that the surface applies to the mass is called the normal force because it's perpendicular to the surface, and in math the word normal means perpendicular. But because this object is not moving along the perpendicular axis, it must be the normal force is just balancing out the perpendicular part of the weight. The normal force is going to equal the perpendicular part of the weight. It'll be 96.33 newtons. All of that, oh, that end looks really bad. All of that is just kind of a little extra for this problem, but it will pay off in maybe some later problems. Okay, let's go back to the acceleration. And this time, we will have the net force equals the mass times the acceleration. But this time the motion is along the parallel axis. So we'll draw the components in that way. Parallel part of the net force is the mass times the acceleration parallel component. And that's going to give us the 67.45 equals the mass, 12 kilograms, times the acceleration parallel component. And then that acceleration will be about 5.62 meters per second squared. Should be worth noting that the acceleration, if we found a value greater than 9.8, there'd be a problem. This object obviously is not in free fall. The surface is kind of getting in the way and decreasing the acceleration. So if we had free fall or beyond, we'd know that something is wrong with this problem.